mechanical translational system. So we are talking about rotational systems now. So coming to the rotational systems. Okay, so coming to the mechanical rotational systems, so these are the rotational systems. Generally, we come across in our regular life. Okay, so similarly, I told you in the last class about uh, torque. So how do you define torque? Torque,
Rate of change of angular momentum.
rate of change of
Angular momentum.
momentum. Any other? Any others? Yeah, torque. Asking you is waste, I think, waste of time.
Moment of force.
Of force. Tau is given by torque. Tau is given by
Force into the perpendicular distance.
R cross F.
force into
The perpendicular distance.
particular distance. So when you apply torque, right? So the object is getting angular rotation. Right. So similar to the terms which we defined. So the basic three elements which we defined for modeling mechanical systems are uh, mass, spring, and dashpot. Okay. Similarly, in rotational systems also we define like displacement is equal to angular. The displacement here there is a displacement along straight line, but here displacement along axis. So angular displacement, and we model it as uh, there it is like mass, but here it is moment of inertia, right? And then spring, torsional spring or rotational spring. Okay, rotational spring, and then here also rotational friction which exists in rotational systems are represented by using rotational dashboard. So three elements. So now here, now let us try to take a case. So now let us take, there is a shaft, right? There is a shaft. So when you apply torque on this shaft, there will be angular displacement theta. Okay, there would be angular displacement theta, right? And now, if the torque can be of rigid, the torque can be rigid or soft. Okay, the shaft. This is a shaft. The shaft can be rigid. So when the shaft is rigid, the angular displacement which is resultant due to the torque is same throughout the shaft. So assumption, if the shaft is rigid, the displacement is same throughout the shaft. But whereas if I assume like when you try to take uh, okay, when you try to take the shaft like this, and then when you apply torque, and if it is it is not non-rigid. It is non-rigid means there will be angular rotation which is different at one end of the shaft and another end of the shaft. So the same thing is what it is given here. Okay, the same thing is what it is given here. Okay, right. So here, if you try to see, this is what the torque you are applying. Okay, so this is what the torque you are applying. The angular rotation, if it is theta 1, and if it is a non-rigid shaft, there are two angular rotations are possible. The angular rotations are not same. Okay, the angular rotations are not same. Right. So in that case, tau is equal to k into theta 1 minus theta 2. Is this all right, all of you?
Yes,
Okay.
good, sir.
So this is rotational spring. And similarly, you have rotational damper. Right. Rotational damper, which is also same. Right. So T is proportional to d by d theta of d by dt of theta 1 minus theta 2. So general rotation, it is B only, the frictional coefficient, B into theta 1 dot minus theta 2. Right. And then moment of inertia. So moment of inertia is, the same Newton second law of motion. We will extend it to rotational body. So the applied torque is equal to or it is proportional to the product of moment of inertia and angular acceleration. So this is, T is equal to J d square theta by dt square. So which we write this way, where J is moment of inertia of the shaft, right? So now let us take this particular system and then you try to model this. Okay, so hmm, yeah, we'll try to take one example. So we'll try to take an example from the book itself. Yesterday, I think. So now let us try to take. So try to solve these problems also. This 4-4. Okay, so mostly I'll be giving problems from these only. Okay, so 4-4, I think you can solve these things. Okay, so now similarly, this also we have seen. Yeah. Yeah. So can you see the screen now? You can see
Yes,
the screen, right?
yes, sir.
Yeah. So the question is, this is the question is, this is P13. So P13, write torque equations of rotational system shown in figure. Shown in figure, and find the transfer function theta of s by t of s.
Sir, can you record this meeting, sir?
Wait. Let me. Okay, so this is one example, and this is another example. So I think better I can solve this, right? Okay. Fourth one. So this is okay. So you can do the rest of the things. So this is what the problem. So the problem here is write the torque equation. Okay. So write the torque equation of this and then find the transfer function. This is what the problem is. Okay. Yeah. Fine. So this is what the problem is. So before that, it is very clearly given in just follow this book. Okay, so here it is given like angular rotations and all the clear cut definition says what it is given. Uh, so rotational motion, then here you have yeah. So this is what here it is given. So you just follow through this. So inertia. Inertia J is considered a property of an element that stores the kinetic energy of rotational motion. The inertia of a given element depends on the geometric composition about the axis of the rotation and its density. For instance, the inertia of a circular disc or shaft of radius r and mass m about its geometric axis is given by J is equal to half mr square. Okay. So which we can write it as, so T of T is J, if you extend the Newton's second law of motion to rotational body, so T of T is equal to J theta T square theta by dt square. So this is what inertia, and similarly you have, okay, similarly here you have different, other elements and all, you just go through. Yeah. So now let us go ahead. So this is what you can see the screen clearly, right? Yeah. So now what we need to do? What is the assumption given in the problem about the shaft? It is a rigid shaft or it is a soft shaft?
Rigid shaft, sir.
Rigid means what? The angular displacement is same throughout the shaft, right? So now we have to draw free body diagram around moment of inertia. So here you have the shaft, right? So the torque is in this direction. So T of T, and the angular displacement is also in this direction, theta of T, right? So the moment of inertia of this shaft is J, right? And now when the shaft is trying to rotate downward direction, there is a frictional torque which opposes this particular displacement. Right. So then the friction would be along with same theta t, or it will be opposite.
Opposite.
So here, so this is TB of T. Okay, TB of T. Right. So now, if you write now the Newton's second law of motion here for rotational body, then T of T minus TB of T is equal to the product of moment of inertia into angular rotation. So d square theta of t by dt square. Is it all right, all of you? Is this clear? Yeah. So now t of t minus tb of t. So tb of t is the frictional torque. Okay, so this frictional torque can be given by b d theta of t by dt is equal to, okay, is equal to, right, is equal to j dt square theta by dt square. So now if you mention like the shaft is having a spring or some kind of thing, and opposes the angular displacement, that also you can consider, but here it is not mentioned, then no need of it. So right, so this is what the differential equation governed by this particular rotational system. So is this fine now? So now if you want to obtain the transfer function t of s by theta of s by t of s, apply Laplace transform. So t of s minus b, tell me now, Laplace transform of, so apply Laplace transform. So then b into s
Yes,
theta
due.
of s minus initial condition. But what happens? So we are not taking initial condition into the consideration, we are neglecting it. So j into s square theta of s. So now if you try to take theta of s here common, which is js square plus bs. The transfer function is given by t of s by t of s is equal, theta of s by t of s is equal to 1 by js square plus b of s. So this is what the transfer function of this particular mechanical rotational system. So is this clear now?
Yes, sir.
So now let us try to take this particular system. Okay, so this particular system. Now help me out. Draw the differential equation governed by this particular mechanical rotational system. Okay, right, and then obtain the transfer function. The transfer function can be anything like, you know, theta 1 of s by t of s, okay, or theta 2 of s by t of s. Now where do you see these kind of systems in real time? You try to see there is a motor and two sides, that there are the pulleys, okay, connected. Did you see these kind of systems anywhere? Tell me, sir, why we why we need to model? Do you find any application of these when
Sir,
you
in vehicles, in cars and vehicles.
are
So motorboats.
floor mill, huh? floor mill, single motor, multiple loads, right? So I think possible I can show you the situations. Can you see this now? And there would be the cases like this is, here you have multiple load, single motor only, no? But one shaft, there are, so this is the cases we can see in our real time. The extension of this only, I think. For one floor mill, you have a rice and you have chili. All the things will be connected, right? Water, access multiple load. I think so. One motor here at one particular side, and then it is connected to n number of this thing. So I think by this time you would have got an idea, right? Application of these things. Okay. So the same situation. You can see here, same situation kinda. I am preparing notes now. But you can see reality, right? So this kind of situations, you have only one motor, but you have right, you have one shaft which is connected to that, multiple loads. This floor mill for rice, this is for jawar, and this is for wheat. So so many things are connected to one particular shaft, so that everything will be rotating at one particular moment. Yeah. Now tell me which type of shaft it is. This is a motor. To the motor, you have two loads at both the sides. Okay. So the motor torque is theta m of t or t of t. Right. Motor is electromechanical system. Input is electrical energy, output is mechanical energy or angular displacement, right? Right. So when you switch on the motor, you know the electrical energy is converted into rotational energy, right? So that is theta of t, and the angular displacement of the motor is theta m of t. Correct. Now this is connected to a load of moment of inertia J2, right? Now this shaft, the displacement here is theta m of t, but the displacement at the end is theta 2 of t. Which type of shaft it is? Rigid or non-rigid?
Non-rigid.
Non-rigid.
It is non-rigid. Okay. And same thing here also, correct?
Yes, sir.
Yes or no? Yeah. So now what we need to do, we need to draw free body diagram around moment of inertia. Okay, or around moment of inertia, right? So now here the motor is having moment of inertia Jm. Okay, so theta of t is applied in this direction. Torque is applied in this direction, which results in a rotation of theta m of t. Okay, and here also the same angular rotation, which is theta m of t. Okay. All right. And when this particular shaft is moving towards downward direction, due to the non-rigid of this particular shaft, there would be a opposing torque due to what? There is a spring here. The spring, when spring is moving downwards, the deformation is represented by using spring. Okay, so when spring is in the downward direction, to get the displacement throughout the same through the same spring, the same thing, this direction and that direction, this end and that end. No. So this spring force and the spring torque will be in opposite direction, right? So this is
Yes, sir.
Tk1 of t. All right. Getting or not?
Yes, sir.
Now, so you are applying torque in downward direction, but the shaft is connected to other load, but the shaft is non-rigid, and this non-rigid shaft is represented using a spring. So when you are applying torque and then the torque is trying to move the shaft downward direction, because of this, this deformation or non-rigidity will oppose the moment angular displacement, right? So there would be one more torque here, right? And this torque is Tk2 of t. Is that understood? That will be in opposite direction, correct? No?
Yes, sir.
Yes, sir.
Is that any rotational means friction given? No, no. Rotational friction is not given. See, rotational friction is be possible if I extend the problem like this. So this is, connected in a valve, and that valve, the shaft has to rotate. So at that time, this would be through friction. That means there exists friction. But that case is not given, so we are not taking that into consideration. Okay. All right. So this is free body diagram around moment of inertia of the motor. Okay. Yeah. So what is the next step? Summation of torques acting on a body is equal to the product of moment of inertia into angular acceleration. So now T of t minus Tk1 of t minus Tk2 of t is equal to, tell me, Jm d square theta m of t by dt square. Is that fine?
Yes, sir.
Now, what is Tk1 of t or Tk? So here Tk2 of t. What is Tk2 of t?
Tm minus T2 of t.
Something else.
K2 into theta m minus theta 2.
K2 into theta m of t minus theta 2 of t. Okay. And what is Tk1 of t? K1 into
M of t minus theta 1 of t.
theta m of t minus theta 2 of t. Theta 1 of t, sorry. Theta 1 of t. Is that fine? So now you know TK1, now you know TK2. Simpler substitution, apply Laplace transform and obtain transfer function. Right. Okay, this is equation number 1. Similarly, we have to write around J2. So this is J2. Right, around J2. So there is an angular displacement theta2, which is in downward direction only. Okay. So spring force, spring force here, Tk2 of T here only. Now, when I draw free body diagram around J2, right? So this Tk2 of T is upward direction or downward direction?
Downwards.
Downward direction. But whereas with respect to Jm,
Upward.
Tk2 of T is upward direction. So here Tk2 of T is downward direction because there is an angular rotation in J2 is due to the spring torque only, no? There is no direct torque acting here, right? Okay. Right. So is there any other thing? No. So Tk2 of T is equal to J2 into d square theta 2 of T by dt square. This is the equation governed by this moment of inertia J2. Is that fine? All right.
Yes, sir.
And J1. So now J1. So now TK1 will be downward direction or upward direction. So here J1, theta 1 is downward direction. Correct? So TK1 of T is also downward direction, right? TK1. So here actually when torque is applied here, the spring torque will oppose the movement. But here the spring torque is downward direction. Is that understood by everyone?
So,
Okay. So this is Tk1 of T. So the Tk1 of T is equal to J1 d square theta 1 of T by square. So this is equation number 3. Now apply Laplace transform of this and you can eliminate the other terms. Then you can get T1 of S by T of S, one transfer function, or theta 2 of S by T of S, another transfer function, or theta M of S by T of S, another transfer function. Any one is what you get. Okay? Is that fine?
Yes, sir.
Now, can you do it now? This one, which is mentioned here.
Sir, could you please clear the point why we get TK1 and TK2 once?
Yes, sir. I did not understand. There is no elongation, no, sir. Then why are we getting something like opposing force?
Yeah. Can you see this problem? Actually, what is there in the screen?
Yes, sir.
Yes, sir.
So this is a shaft. Okay, this example you try to take. This example you try to take. Now this is the same shaft, but the angular displacement at the both the ends same or different.
Different.
That different, sir. Yeah.
So it is a rigid body or non-rigid body.
Non-rigid.
Non-rigid.
It is a non-rigid body. Accepted, no?
Yes, sir.
Torque is applied here. Motor is connected somewhere else here. Okay.
Yes, sir.
Right. And this is one load having moment of inertia J1. Okay.
Yes, sir.
Between these two, there exists a frictional torque. Okay.
Okay. Yes, sir.
Right. And now this results in one more angular displacement theta 3. Okay.
Yes, sir.
Correct? No?
Yes, sir.
Right. So now direct torque is here, right?
Yeah. Yes.
But
Yes,
is
sir.
there any torque applied here?
No, sir.
But this happens due to
Because it's connected to J2.
connected to J2. Correct? No?
Yes.
Right. Now, the same thing earlier in translational motion, there is a body of mass m1, there is a body of mass m2, and they are connected through spring and some, let us take frictional thing. So this displacement is x1, force is applied here, correct?
Yes, sir.
And here the displacement is x1, here the displacement is x2, correct? No? When
Yes.
this body is trying to move in this direction, this spring force and frictional force will oppose the movement, right?
Mm. Yes.
Right. With respect to this body, this is opposite direction. But with respect to this body M2, this forces are in this direction or in this direction.
Supporting. Yeah.
Towards M2, sir.
Huh?
Towards M2.
Towards
Support.
Yeah, so then this T or Fk is in this direction and then Fb is also in this direction. That is true. This is M2 and this is M1. Accepted, no?
Yes, sir.
And is there any question about Fk and Fb with respect to M2? No, no.
No, 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 sir. Here this is clear. Yeah.
Same thing, extension to rotational body. Can you see my hand? The camera where it is focusing also, I don't know. Unless now let me face you. Yeah. So you can see my hand, right?
Yes, sir.
Yes, sir.
This hand is trying to move in this direction, okay?
Mm-hmm.
But there is a opposing, there is something like oppose, which will oppose this movement, right?
That's torsional strain, no, sir.
That is the torsional, there's a spring, okay? Spring torque, okay?
Mm.
That is spring torque, man, okay? See, this is a wire, right?
Yes, sir.
The spring torque. Now, this spring torque at one end will oppose, another end will help in angular rotation, right?
Yes, sir. One end will up. Yeah. Mm.
Correct, no? Here, when I applying torque here, it will oppose here, but it is also moving. Here also it is moving because of this is in same direction, no?
Yes, sir.
Same thing only we are taking, no?
Yes. Mm-hmm.
Understood. See now, this is a hand. At the end, I'm applying torque. When I'm applying torque, it is no here it is opposing. Here it is opposing, but this is also moving, right? Here it is in opposite direction, but here it is in same direction, right?
Mm. Yes, sir.
Same thing is what we are trying to take, no? TK1 and TK2. Shall I solve one problem, one more problem? Right? No time, man.
Yeah, understood, sir. Like, yeah, understood right now. Yeah.
One more small concept is there. That small concept now needs saying. The prescribed book, we correctly it is giving. Can see screen now?
Yes, sir. We can see the screen. Yeah.
So what is the problem? Earlier problem and this problem are difference?
We have extra B2, B1 and B2. Those
No,
damping.
this is fixed in the wall, right?
Yeah.
Both the ends are fixed in wall. This kind of situation we can see in real time or not? Floor mill. Not getting exact this thing, but floor mill single axis multiple load fixed to wall. I don't know whether Google gives us. This the same thing I'm getting, but it is fixed to a in the end one end. Without moving, we will fix it to a wall, right? One shaft. I used to see somewhere in village, but I don't know. No, not I. Whether you go to floor mill anytime. Grinder is available at home itself. Okay, all right. Any industrial system you try to see. Okay, right. So this is understood now, no? And free body diagram around motor is same, no?
Yes, sir. It would be same for motor, but for J1 and J2, additional.
Yeah, for J1 and J2. So let me do it for one so that you can do it for any other thing. Okay. Yeah. Now let us take about J2. So J2 moment of inertia here, this see. And now when theta T of T, in this direction, theta 2 is in downward direction. Theta 2 of T is in downward direction. So there exists one more torque which is TK2 of T here, downward direction. And now coming to the frictional torque, TB2, when it is moving, this theta 2 is in downward direction. This is theta 2. Then TB2 will be in same direction or opposite direction?
Opposite.
Definitely opposite. So this is TB2 of T. Okay. Friction will oppose the movement, right? Okay. So this is the free body diagram. Tell me the equation now. Theta 2 of T minus TB2 of T is equal to J2 T square theta 2 of T by Dt square. This term is extra now here, right? Gone. This is TK2 of
K2 will also.
TK2 of T. Correct, no? Correct, no?
Yes, sir.
What is TB2 of T?
B times
Total
d
friction
theta 2 by
force.
dt.
D theta 2 by D.
dt.
Correct. Now you apply Laplace transform and obtain transfer function. Okay, so this is what the problem given. So can you do it now?
Yes, sir.
And similarly, here, what is extra here?
Friction coefficient at near to wall. It is not directly connected to wall. Other side near J2.
That is the thing. Okay. So you can do it. Now you can do it for this also, right? Hmm?
Yes, sir.
So like this, you can do it. And the next one is gear, but I think too much into mechanical. This is also very interesting actually. If you want to do any research paper, I'm telling you, your seniors, they are approaching for recommendation letters for doing their MS. Ultimate goal of any student of NIT is earlier after completion of BTech they used to go for MS, but these days the trend is your bank balance matters to do your MS. So what you do generally is 2 years you work here in India, get at least 5 to 10 lakhs of bank balance or 20 lakhs of bank balance, and then you fly US. That is ultimate goal. 50%, more than 50%. Then at that time they will see your GRE score and then your research papers which you have here. So if you want to do research paper, then definitely you should have solved a paper and then proposed a paper, right? So I think one of your senior last time he worked and then he presented one research paper international conference at MNIT Jaipur. Right. So if you have research paper, then only I will give recommendation. I will not give recommendation. So any faculty's reputation depends upon their citations. The moment you type the name in Google Scholar, there the right citation means how many number of your papers are referred throughout the world. It is called citation. If you write one research paper, how many people, other people, they are referring your paper when they are considering their work. That is called citation. Okay, how many number of sites? So that citation, when the foreign universities they see recommendations given by the faculty of any institute, whether the faculty gives correct or not, they will judge by their citations. So if at all, if you want my recommendation, definitely you should have at least a research paper. And during summer intern, summer we offer internships. So generally, if you come here in summer and then if you work and that results in a research paper, where you can submit on an international conference, then only I'll give recommendation. So at that time, little bit extra you need to work it out. Right. So the syllabus here, it is here only. No, some extra work need to be done by you. Right. So now let me give you a few things. What is the time now? I think time is over. What is the next period, Varun?
Transmission lines and electromagnetic waves.
Yeah.
Is
So
that level?
here, uh, mechanical system. Mechanical system means car suspension system. Car suspension system. Suspension system. So this is full car. Okay, modeling on control active suspension full for full car. So now if you try to see, you will get a research paper here, which is in 2009 actually. This paper is in 2009. This paper is in 2010. And now if you try to see images regarding this, Yeah. So now this is full car actually. So this is a full car suspension and tire and all. Okay. So this is actually this is tire suspension system. So sprung mass. Okay, and sprung mass, and then there is a road bump. How the vehicle moves and all. These kind of things they are given. Try to see, and then try to download few research papers and try to solve them of this thing. Okay. So possible in next class I will be elaborating on this, and we will be using MATLAB Simulink to solve these things. Okay. Any questions, please? Any questions, please? If you have any questions up to in this topic, you can ask me. And now you see, the moment you see the authors written by different papers, this is in 2019 only. The authors you see Nanjing University, not from India. So generally you will not focus now, but the moment you come to recommendation, I'm telling you, I will not give recommendation without having research paper with me. Okay, I'm telling you. I'm very, frankly, I'm telling. And you try to see what are my Google citations, 924 by this time. And my H index is 17. Means at least 17 papers of me are referred by at least 17 minimum number. One paper is referred by 120. Okay, so you have to know the importance, and then you have to focus it up. So this is one paper. So like that, not only book knowledge, we have to refer the other things also, and get the things. This is a paper. So this is a mechanical system given, right? So their values are also given. I'm telling you, Varun, I will be giving questions like this in the examination. Okay? Yeah. So we'll be meeting in the next class. Take snapshot of this and try to see. Try to download this paper and how they modeled and all. You try to understand. Okay. And what equations they got, whether we get the same equation or not. So these things I will be discussing in the next class. Okay, fine.
Sir,
Yeah.
sir, for recommendation, you said we need a paper under use, sir, or generally?
For me, condition is this.
Sir.
For others also, if you work a project with them, they will give. Otherwise,
Okay.